everybody. I wanted to make sure that you had solutions to this free response problem set that I handed out on Thursday. Again, I'm going to feature the AP solutions, but in case you kind of want some more explicit answers on what's going on, I thought I'd just go ahead and do that here. So let's draw a free body diagram for the block in part A. So we have mass of the block times g. And remember, the normal force goes perpendicular. And let's see, we have a rope pulling it upwards like this, so we'll call that the tension force. And opposing the motion of the block is a friction force right here. Please note V is velocity. That does not belong in a free body diagram. Also, let me just take a quick skim here. We've got MB, MH. We see the letter mu K there, so this is a kinetic friction force. And it appears that MH is falling down this way. So we have a M hanging times G. And we have a tension force going upwards like that. Now, let's just double check. Whenever I see a question like this, the first question I want to ask is, are the forces balanced or unbalanced? They're balanced if it's either at rest or moving at constant velocity. It seems that we're moving at constant velocity here. Let me just skim and confirm this. It says right here, constant speed, excellent, so each mass is moving at a constant velocity. And so we're going to derive an expression for the mass of the hanging object using this idea here. So first, we're going to say, let's write down the equation for the block. So in the horizontal direction, we're going to say T minus F equals 0. We're also going to have the normal force. And you know what? I want to be absolutely clear here. I don't think I set that up right. I need to split. It says do not add anything to the figure in part A. That's really annoying because I think you all know what's going on. Is right here, I need to set up sine and cosine components because I'm on an inclined plane. So what I'm going to have to do with this annoying thing to make the AP happy is draw a new free body diagram. So I'm going to have MBG, I'll have tension, I'll have the friction, and this is exactly, sorry, that's the normal force. And then I have the friction going this way. This is exactly why I had you memorize this proof. So this is mg cos theta, and then I'll have mg sine theta here. Awesome. So we want the mass of the hanging object. And so let me just make sure I set up my equations here. So for the hanging object, I'm going to write down mh times g minus t equals 0. It equals 0 because we're moving at a constant velocity, constant speed, and that means things are balanced. Now, for the block, we're going to say t minus f minus mg sine theta equals 0. And you know what? Let me add a little subscript there to indicate that we are talking about the block. Continuing on here, we're going to say T minus. Now, friction is mu times the normal force, so let's just get that set up real quick. We know that the normal force minus mg cos theta equals 0. And so using friction is mu times the normal force. Sorry. Fn equals mg cos theta. So that means the friction force is going to equal mu k times mg cos theta. So what that tells us is the tension force T minus mu k mg cos theta minus mg sine theta equals 0. So that gets us a tension force equal to mg mu k cosine theta plus sine theta. And that's mass of the block. Now I can substitute into here. So when I put this equation, I'll call this equation 1 and this equation 2. When I put equation 1 and 2 together, I'll end up getting mbg times sine theta plus mu k cosine theta equals mh times g. I'm basically saying that the tension expressed here equals the tension expressed there. The g's cancel. And so finally, I have that mh equals mb sine theta plus mu k cosine of theta. All right, so that's part B, A, and B right there. Let's just take a look at part C. So now we're saying while the block is moving up the ramp, the hanging object is moving downwards, the string is suddenly cut. So the block acceleration immediately after the string is cut, let's just be clear. So we don't have the tension. The block is moving up the ramp. The hanging object is moving down. The string is cut. We want the acceleration of the block immediately after the string is cut. So let's be clear. The forces, again, we've got mg, we've got fn, we've got now mg sine theta, and the friction still goes this way because we just suddenly cut off the tension. So what that means is this is now 0. So what's going to end up happening is negative f minus mg sine theta equals m times mass of the block times a. And you can set up a little t here like you did before, but this is going to equal 0. And remember, friction is mu m b g cos theta minus, and we'll take away from there the mg sine theta part, and that's going to equal mb times a. So if we want the magnitude, which is another way of saying absolute value, the acceleration is going to end up being mbg times sine theta plus mu kinetic g cosine of theta. All right, now the direction of the acceleration of the block immediately after the string is cut down the ramp, and we see that from the free body diagram. Okay, and again, it's just to see the free body diagram. And lastly, the acceleration of the hanging object immediately after the string is cut. Well, we cut the string. The free body diagram used to be t and mh times g, but this equals 0 now. So we have mhg equals ma, mha. So a is just equal to g for that. All right. Now it says, assume the block is moving up the ramp at 2 meters per second when the string is cut. Calculate how far the block travels up the ramp from the time the string is cut until the block stops, assuming there's sufficient distance on the ramp. There's a couple ways to do this. I'm going to do the following. I'm just going to basically say v squared is v naught squared plus 2 times a times x, which is the distance up the ramp. So that 0 squared equals 4 squared plus 2 times negative, I have it here. So you know what? I forgot this a that mb should cancel, so it's just g sine theta plus mu k g cosine theta. All right, so that's going to be negative g. I'm just copying the acceleration from part C. So that's g sine theta minus mu k g cos theta right there. And so let's go ahead and actually calculate the acceleration here. When we actually put in the number, that's going to end up being a equals 10 times the sine of 30 plus 0.1 times the cosine of 30. And that's going to give us 5.87. By the way, it's 5.75 if you use 9.8. So I'm going to put here 0 squared equals, oh my gosh, 0 squared equals 16 plus 2, and there's an x there, times the acceleration, which is negative 5.87 times x. And when we simplify that, we're going to end up getting here, let's see. So that's v squared. That's 2 squared divided by 2, 5.87. They're getting 0.38 meters, and I got to double check why. It's because I got to correct this. It's 2 meters per second squared, so 0 squared equals 2 squared plus 2 times negative blah, 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 blah. And so this ends up being 4 plus 2 times blah, blah, blah. And that's how we're getting 0, sorry. And since I'm using 5.87, this is going to be 0.341 meters up the ramp. All right, so I believe that's problem number 1.